All right, I guess we can go ahead and get started for today. Excuse me. So the plan is to go ahead and go over this past exam, the exam we just took, show you how I would go over the problems, how I would solve them. And that way, when you look over your test, what is graded, and you'll see, what you got wrong, what you got right, and any questions you may have about why things were marked wrong. Hopefully this will be able to help, as well as I said a little bit ago, help to, when it comes time for the final exam, because of course, all of these topics will be on the final exam since it's cumulative. So we have to remember how to do these problems later on. We're not just going to stop just because we move on to a new topic. So that's the plan. We'll work on this exam. And then on Friday, we will start into the next topic, which will be light and optics. Things like lenses and mirrors, how does light work, and all that kind of stuff. So let's go over the test. First of all, I've not graded them yet. I will be grading them today and tomorrow. So hopefully by Friday, they'll be all graded and you can check them out on Canvas. But generally speaking, for these tests, first of all, on the first page at the top, I usually try to put any of the constants and things like that you may need to use throughout the test. Instead of putting them in each question where they're important, I just put them at the beginning. That way you can always reference them later on if you need them. Now, you won't always need them. Sometimes I give you a bunch of constants and maybe none of the questions needs one of the constants, but they're there in case you do need them. In this case, I gave the density of water and the atmospheric pressure, the pressure of the atmosphere by itself. All right, so to get started, first question, a battleship is placed in a freshwater lake. A freshwater lake just means it's water. It's not salt water or anything like that. It's found that 27% of the ship is submerged in the water. Calculate the density of the battleship. So for this type of question, I'm thinking of using the equation percent submerged is equal to the density of the object over the density of the fluid. I want to know the battleship, so that's the density of the object. So I go ahead and I solve this. Density of the object is the percent submerged times the density of the fluid. So those are the two pieces of information I need. How much of the battleship is submerged in the water? And is this water? Is this some other fluid? So here I'm told 27% of the ship is submerged. Always be very careful when you have a question like this, because sometimes the question gives you how much is under the water, whereas others, it's how much is over the water, floating on top of the surface. In this case, it tells us how much is submerged. So that's perfect. We could just put it in directly. We're told 27%. And that means in decimal form, it's 0.27. So 27% of the battleship is submerged in what? It is submerged in fresh water. And so I use the density of water, 1,000. And that's all there is to it. 0.27 times 1,000, pretty easy. That's just 270 kilograms per cubic meter if you wish to use the units. And of course, we can ask if it makes sense. Remember, the theory is an object sinks if its density is greater than the fluid, and an object will float if its density is less than the fluid. Here, the density of the fluid is 1,000. Our battleship is floating on the surface, although some of it is under the water. It's not sinking, it's floating. So I would expect that the density of the ship should be something less than 1,000. And indeed, we find that it's 270, that's less than 1,000, so I can be happy with it. Are there any questions about this particular problem? All right. Next question. A rock is thrown into a pond. The rock sinks down 8 meters to the bottom of the pond. Okay. And we want to know what's the pressure on the rock, but we're asked two different ways. Number one, what's the gauge pressure, which is just how much pressure does the rock feel more than if it's just sitting there in the atmosphere. So we know it's going to feel the atmospheric pressure, but since it's now under the water as well, it's going to feel some extra pressure. And so the question is, how much extra pressure does it feel? That's what the gauge pressure is. And I know that there's a relationship between the pressure on an object and how deep it is underneath the water. And that is the pressure is rho times G times H, where rho is the density of the fluid, of course, and H is how deep you are. Well, we're in a pond, so that means we're in water. So I know rho is the density of water, which is 1,000. G, that's just the acceleration due to gravity, that's 9.8. And then H, that's how deep is my rock. It's 8 meters under the surface, so the depth is 8. So plug all these numbers into my calculator, and I get 78,400 pascals, or if you want scientific notation, you could just say it's 7.84 times 10 to the 123, 4 pascals. Either one of these answers is fine. So that's the gauge pressure. That is, if you're a scuba diver or something, and you have your apparatus on your back and you dive down 8 meters, what would the apparatus say is the pressure pushing on you? It would say this much. Of course, we know that that's not the only pressure that's squeezing this rock. There's also the fact that even if it weren't under the water at all, it would feel some amount of pressure because it's in the air, it's in atmosphere. That pressure is always there regardless of what you're doing. And that's what's called absolute pressure. Absolute pressure is the pressure due to the atmosphere, which is always there, plus whatever gauge pressure is also acting. So I could say absolute pressure is the gauge pressure plus the atmospheric pressure. Well, I already figured out the gauge pressure. That's 7.84 times 10 to the 4th. And then atmospheric pressure, well, that's just a constant. That's just a number for the Earth. And in fact, of course, this number depends on where you are. Are you up in Denver, a mile up on a mountain? Are you in New Orleans, underneath sea level? This pressure will change, but we're using the average atmospheric pressure. And that's given there at the top as a constant, 1.01 times 10 to the 5th. So 1.01 times 10 to the 5th. And so there we go. That's what I want to add, 1.01 times 10 to the 5th plus 7.84 times 10 to the 4th. And I get 179,400 or 1.79 times 10 to the 5th pascals. Again, this absolute pressure should be something more than the atmospheric pressure, should be bigger, because you're also adding in the fact that you're under the water. So you have the atmospheric pressure plus some extra bit, and that's indeed what we find here. So any questions about this problem? The pressure-depth relationship.
I actually got 1.79. I got 1.794. Would that be fine?
Just 1.794 without the 10 to the 5th?
No, with 10 to the 5th.
Oh, yeah.
I did it in both. I did it in both scientific notation and regular notation.
Yeah, that's fine. That's fine. And if there's some slight rounding or some slight thing like that, that's perfectly fine. It's not like, this is why I don't do computer tests or computer homework where the computer is the thing grading you. And so you have to be worried about having exactly the perfect number. if I'm looking, first of all, I'm looking at your work to see what you're doing. And if the work is fine, and then of course the number is off by just a little bit, and maybe it's for rounding issues or something, that's no big deal. That's right to me. So yeah, that sounds perfectly fine. All right, number 3. Calculate the percent submerged of an object if the density of the object is 2200 and it's placed in a fluid whose density is 1500. All right, well, that's very similar to the first problem, another percent submerged type question. So percent submerged is the density of the object over the density of the fluid. In this case, I want to find the percent submerged. So this is really easy. I don't have to do any algebra. All I have to do is plug my numbers in. Making sure my units are okay. I'm not having some weird units somewhere. That's always something you want to be careful about is the problem about plugging numbers into the equation, or is the problem a trick to make you have to convert a bunch of stuff? In this case, it's straightforward. There's no converting necessary, but always keep that in the back of your mind, especially when you're on a test and it's timed. It's easy to overlook little things. But here, everything's fine, so we just plug the numbers in. The object is 2200. The fluid that the object is put in is 1500. So I just divide these two, 2200 over 1500, and I get 1.467. Now, this is perfectly fine for a number. Okay. If you're doing this and you get this answer and you either box this or you say this means in terms of percentage 147%, that's perfectly fine. Now, if we take it further and investigate what the heck this means, this is kind of weird. We have a percentage which is more than 100. Of course, that doesn't make sense in the real world. You can't have more than 100% of an object. So really what this is telling me, if I'm going to act as a physicist and I want to try to, or a scientist in general, and I want to try to figure out what this means, what this tells me is this object sinks. The full object will be under the water. Anything at 100% or more means the object sinks. And in fact, if we look at the densities, the object has a density of 2200, the fluid is only 1500. That means that the object has a bigger density than the fluid. And from what we recall in terms of the concepts, to sink, your density must be greater than the density of the fluid. And that's what we have here. The object just has a bigger density, so this object sinks. So if you're going to try to figure out what this tells you, it just means the object sinks. But in terms of the answer to this question, if you put 146 or 147% or 1.46, whatever, that's perfectly fine. You don't have to go further than that. Okay. So that's number 3, another percent submerged. In this case, it just happens to be that the object is a sinking object rather than a floating object. And that's why we get a weird percentage. All right, number 4. Number 4, we have a pipe system. Water is flowing through a pipe with a velocity of 10 meters per second. The pipe has an initial radius of 60 centimeters. The pipe eventually raises up by 20 meters. Calculate the difference in pressure between the initial part of the pipe system and the end. All right, well, this sounds like Bernoulli. You have a pipe, water flowing through a pipe. The pipe can either move up and down or it can change size, and we want to know about the pressure. Well, before I go ahead and do the calculation, let's draw what this may look like. If I were to draw this out, we have a pipe. The radius of the pipe is 60 centimeters, so R is 0.6. And the velocity is 10 meters per second. Then we're told the pipe raises up by 20 meters. So, okay. The pipe goes up 20 meters high and continues on. And then I want to know over here at the end, what's the pressure or what's the difference in pressure? So there's P1 over here, there's P2 at the end, and I want to know what the difference in pressure is for this system. Now, this is a very good question to note when there's information in the problem that you may not need. It may not be important to you, certain piece of information here. And let's see. Bernoulli says P1 plus 1/2 rho V1 squared plus rho GH1 is P2 plus 1/2 rho V2 squared plus rho GH2. So this gives us 3 pieces of information per location. The pressure that's at that location, P. Then there's a term about the speed of the fluid, and the speed of the fluid has to do with the size of the pipe. And then there's a term about how high or low the pipe goes. Does it raise up? Does it fall down? Does it stay straight? So at each location, we have all 3. Now notice this particular pipe system, what happens? The only thing that happens to this pipe is it goes up 20 meters. There's nothing here that says anything about the pipe changing size. We're not told that the velocity changes. All we're told is that the height changes. So what that means is, even though I have information here about the speed of the fluid and the radius of the pipe, so it makes you think, I'm going to be using continuity soon. The fact that the question doesn't say anything about the pipe changing to a new radius tells you that the speed doesn't change. The pipe is just the pipe. It just goes up to the second floor. So really, I don't need this term and I don't need that term. If the pipe did change size, then of course I would need both of those terms, because then the velocity is going to change. But here, the only thing that changes is the height. So I only need to keep the terms with the height in it. So if I continue, I say, what is it I'm looking for? I want the difference in pressure. And difference in pressure means P2 minus P1. The change in pressure, the difference between the end and the beginning. So if I want P2 minus P1, that means P1 I have to move to the other side, and that's why it becomes negative. And then I want P2 minus P1 by itself. So this term over here, rho GH2, I have to bring to the other side. And when I do, he becomes negative. So now that side of the equation is rho GH1 minus rho GH2. And now we have our equation. The left side, that's what I want. P2 minus P1, that's called the difference in pressure. The right side, that's where I plug my numbers in. What do I know? Well, we're talking about water. Water has a density of 1,000. So we have 1,000 times 9.8 times the original height. Well, I don't know the original height. Here, all I know is that wherever it was, it goes up 20 meters. And remember, we discussed in class that when you have this type of situation where you're not told the exact locations, you're just told how the location changes, then you can set one of the locations to be 0 and the other one to be whatever the change is, because it'll make the numbers go by quicker. One of the terms will be 0. And in this case, because I raise up by 20, I'm going to call the initial location H1 being 0, and the second location, H2, being 20 more than that, which is 20. So H1 here is just 0. The next term, rho 1,000 times G 9.8 times H2, which is 20 above H1, so that's 20. And there we go. I now have my equation with all the numbers plugged in. This term, of course, is just 0. So all I have is 1,000 times 9.8 times 20. And that's 196,000 pascals, or 1.96 times 10 to the 1, 2, 3, 4, 5. Negative. The answer is negative. So the change means that if you were to check the pressure at the top, it would be 1.96 times 10 to the 5th pascals less than the pressure was at the beginning. So this is important. This is a Bernoulli problem, so we know to use Bernoulli's equation. But on the one hand, it's easier because not everything in the system changes. The size of the pipe doesn't change, so all the terms that have to do with velocity just drop away. But on the other hand, it's tricky because the question tells you about the velocity, so it makes you think you may need it. But at the end of the day, there's nothing here that tells you that the radius changed. The pipe didn't change size. So that should lead you to say, okay, even though I know what the velocity is, the velocity won't change. So 1/2 rho v1 squared will be the same number as 1/2 rho v2 squared. And thus, when you manipulate the algebra, they just cancel out. So are there any questions about this problem? I think of all the questions, this might be the place where people would get tripped up the most, purely because the way the question is posed makes you think you need more information. That's what's given. And in fact, I got several students email me and ask, hey, you didn't give the radius, the second radius in this question. Thinking, you know, of course, I made a mistake, which believe me is possible. And that's why I ask you all when you're taking these tests, if you have a question about the problem, feel free to email me because it's possible I made a mistake. I forgot to give a number. But in this case, there was no mistake. Even though I gave you a whole bunch of information about the system, only some of it changed. And you only have to worry about the stuff that changed. So all the other stuff is just meaningless to the actual calculation. All right, question 5. Another pipe system, water flows through a pipe with a velocity of 25 meters per second. The initial radius of the pipe is 20 centimeters. The pipe eventually raises up by 10 meters, at which point the pipe enlarges to a diameter of 2 meters. Calculate the difference in pressure between the initial part of the pipe system and the end. All right, well, this is very similar, nearly identical to the last question. This time, however, let's draw it out again. What do we have? A pipe system. It's going to be moving up. So here we go. Here's the initial part of the pipe. The radius, the initial radius, R1, is 20 centimeters. Remember, you need to be in meters for all these units. So I have to convert to 0.2. The velocity of the fluid, of the water flowing through this part of the pipe, is 25 meters per second. Then what happens? The pipe raises up by 10 meters, so it goes up again. Oops. Okay. And then the pipe enlarges to a new diameter, so it's bigger. At which point it ends, and I know that here, the diameter, the full size D, is 2 meters. And then, of course, as I said, this is 10 meters above the bottom. So there's my pipe system. Water's flowing in, goes up to the second story. The pipe then enlarges to a new size. And what do I want? The difference in pressures. So I get back to Bernoulli. P1 plus rho GH1 plus 1/2 rho V1 squared is P2 plus rho GH2 plus 1/2 rho V2 squared. Okay. Do I need all of these terms? Well, I need the height term because the pipe system moves up by 10 meters. So I need to keep height. Velocity term, the pipe changes size. So I need to keep the velocity term. Okay, so there's no term I could cancel out this time. I need everything. What is it I'm looking for? The difference in pressure. And of course, difference in pressure, as before, just means P2 minus P1. So I'm going to bring P1 over to one side, and everything else goes on the other side. P2 minus P1 equals. We'll have rho GH1 minus rho GH2, then plus 1/2 rho V1 squared minus 1/2 rho V2 squared. So when you move the terms around, getting the P's on one side, everything else on the other, it comes out like this. And now all I have to do is plug numbers in. Do I have all the numbers here? Well, rho, that's 1,000 because we're talking about water. G, 9.8, H1, 0. So actually I could go ahead and cancel out H1 because H1 I'm going to set to 0 since that's the lowest point. H2 is 10, so I have that. V1, 25, I have that. V2, I don't know. I'm not given V2 in the question. So I need to calculate what V2 is. So I switch over to a new calculation. I leave this alone for now and I say, okay, how do I calculate the new velocity? I use continuity. A1 V1 is A2 V2. I'm looking for V2, so V2 is going to be A1 over A2 times V1. All right, what's A1? The area of the first part of the pipe. I know the radius, and it's pi r squared. So it's pi times 0.2 squared. A2, that's the end of the pipe. I don't have the radius, I have the diameter. So I need the radius to calculate the area. Well, the radius is just half the diameter. So diameter is 2 meters. Divide that by 2, it's 1 meter. So it's pi times 1 squared. Times the first velocity, which is 25. So there we go. 0.2 squared divided by 1 squared times 25 tells me that the velocity in the second part of the pipe is 1 meter per second. All right, so I now know what the speed of the fluid is in the second part of the pipe. I asked myself before I use it, does it make sense? Well, remember the rule. When you constrict a pipe, you make it smaller, the velocity goes up. It goes faster. If you enlarge a pipe, the velocity goes down. The fluid moves more slowly. Here, I've enlarged the pipe. So I went from 25 meters per second down to 1. That makes sense. It did get slower. So I'm free to go ahead and use it without worry. So now I plug all my numbers in. Minus 1,000 times 9.8 times H2, which is 10 meters, plus 1/2 1,000 times V1, which is 25 squared, minus 1/2 times 1,000 times V2 squared, which is 1 squared. And now there's my equation. I plug all this stuff in my calculator. I have 1/2 1,025 squared minus 1/2 1,001 squared minus 1,000 times 9.8 times 10. And I get the difference in pressure is 214,000 pascals, or 2.14 times 10 to the 1, 2, 3, 4, 5. And there we go there. So this is more of a full Bernoulli problem. We have a pipe system, water flowing through the pipes. The pipes both change size and location. So I have all the terms here. I set up Bernoulli, calculate what it is I want, which in this case is difference in pressure. And now I have my equation sitting there. One of the terms I don't know because I don't know the velocity in the second part of the pipe. So I move over to continuity equation to be able to calculate how will the velocity change since the pipe size changed. So I set up little continuity equation, plug my numbers in, and I get my answer. I find out that the new velocity will be 1. Now that I know this velocity, I plug it into Bernoulli, and I have my full equation, a whole bunch of numbers that I plug into my calculator, and I get my answer. So any questions about this problem? So this is as hard as a Bernoulli problem gets for us. It's the full thing. Yeah, what's up?
So I remember, I think we did it in other problems, but I kind of did it this way. Is it okay if we like distribute the
Factor.
last row? Yeah, factor
Yeah,
out like
exactly.
yeah.
I'll go ahead and write it down exactly what you're saying. Good. It's actually faster to do it that way. I didn't here just because I wanted it to look as straightforward as possible. But if it were me in my own little notebook doing this, I would do exactly what you said, which is notice right here, this part. What I could do is I could say, hey, this is the same as 1/2 times rho times V1 squared minus V2 squared. So instead of it being like two different terms, it's one term with this little binomial up in there. And so that's 1/2 times 1,000 times 25 squared minus 1 squared. Yeah, that's perfectly fine. And in fact, when I just did it on my calculator to get this answer, that's what I did, just so that I wouldn't have to type in 1/2 times 1,000 two different times. But yeah, that's perfectly fine. As long as the algebra of it doesn't confuse you, you're more than welcome to factor it. That's a fancy way of doing it, which is good. Nice. Any other questions? All right, we're on our last one. Let me move this out the way. Last question. A sphere of radius 20 centimeters is placed into water. Calculate the buoyant force which acts on the sphere. All right, this sounds like Archimedes to me. The buoyant force, if we remember Archimedes' principle, there were several relationships we had to know. But at the end of the day, what we found was that the buoyant force is equal to the weight of the water displaced by the object. Okay. Now, obviously, this question doesn't tell me the weight of the water displaced, but rather I can figure out what that is by saying the weight is rho times G times V. I'm sorry, rho times V times G. Okay, remember, weight is mass times gravity. And mass from the density equation, mass is density times volume. So the weight of the water is going to be the density of the water times the volume of the water times G. Now, that's pretty good, but I don't know the volume of the water. I get the density of the water, of course, I know that's 1,000. G is 9.8, but the volume of the water I don't know. However, there was a second relationship that said that the volume of the fluid displaced is the same as the volume of the object. So I could rewrite this as the density of the fluid times the volume of the object times G. Now, at first, this doesn't seem to be helpful because I also don't have the volume of the object, but I can calculate that because I'm told a few things. I'm told this is a sphere and I know its radius. And I know that the volume of a sphere is 4/3 pi r cubed. So 4/3 times pi times the radius of this sphere is 20 centimeters. Again, you have to be very careful to convert. So it's 0.2 cubed. So 0.2 cubed times pi times 4 divided by 3. And I get a volume of 0.0335 cubic meters. So now I know the volume of the object. I could just go ahead and plug all my numbers into this equation. The density of the fluid is 1,000. That's water. The volume, 0.0335 times 9.8. So I'll plug all this in my calculator and I get that the buoyant force, which acts on the sphere, is 328.4 newtons. So one thing I could say, of course, that's the answer, and that's as far as you have to go. But if you're going to investigate it a little bit, what this would tell you is if the sphere that you're putting into the water weighs more than 328 newtons, then the sphere will sink. Because remember, what makes something float or sink is whether the buoyant force can overcome the weight of the object. If the buoyant force is more than the weight, then of course the object will float because there's more force pushing up than there is pushing down. If the object weighs more than the buoyant force can handle, then even though the buoyant force is trying to lift up, it's not enough, so the object will sink down to the bottom. And so here we know the buoyant force which would act on a sphere like this. So all we have to do if we wanted this thing to float, for instance, is to make sure that whatever object or whatever the object is made of, its weight will be less than this number. So if this is some kind of a boat or a buoy or something like that, then we'd say, okay, what can we make this sphere out of such that its weight is less than 328 newtons? That way the thing will float in the water. So just kind of an investigation into what this would tell you. So any questions about buoyant force and Archimedes' principle?
Dr. Rossman,
Yeah,
I have a question about number 2.
sure. Number 2. Yeah, what's up?
So you know how it says calculate the gauge pressure, and I have as the gauge pressure formula being the total pressure, subtract the pressure on the ATM.
Yeah.
So how, because I got the same answer you had, but I subtracted it from the I keep saying ATM. I subtracted that and the different number, but I got the other answer you had.
Right. So, okay. Yeah, the equation you're talking about is actually this equation. But if I rewrite it so that I solve it for gauge pressure, it says gauge pressure is absolute pressure minus atmospheric, right? That's the equation you're talking about. These are the same equation. Now, if you were to just use this equation, then you'd need 2 pieces of information. Number 1, you'd need the atmospheric pressure, but we know that, that's given right there at the top. But then you'd also have to know the absolute pressure. But there's nothing here that tells us the absolute pressure. This equation, the pressure-depth relationship, what it tells you is the gauge pressure. Because, in other words, if you were to say, okay, I have a rock and I'm going to throw it into the pond, but I haven't thrown it in yet, it's at the top, it's on the surface of the pond, what would be the pressure on it? Well, if I use this equation at a depth of 0, because it hasn't gotten into the water yet, I'd get a pressure of 0. But I know that a rock that's sitting in the air before it gets to the water feels atmospheric pressure. So that tells me this equation must be an equation of gauge pressure, which I had talked about in a previous lecture. This was always gauge pressure. Now, once we know the gauge pressure, we could talk about absolute pressure, because all we have to do is include atmospheric. Or the other way of saying it is, if I happen to know the absolute pressure for some reason, then I could just subtract off atmospheric to get the gauge pressure. But for this problem, I don't know how to find absolute pressure by itself. The only way I know to get absolute pressure with this problem is to first calculate gauge pressure and then add in the effect of the atmosphere. And that gives me absolute pressure. So does that make sense?
Yes, it does. Thank you.
All right. Any other questions about the test?
Can you show the answer to question 3?
3, yes, ma'am. Of course.
Okay, thank you.
Mm-hmm. Any other questions for me about the test? All right, well, that's all I have for today. Obviously, the class is almost over anyway. So next time we are going to start into our next topic, which is light and optics. And I think we're going to go ahead and finish out the semester with this topic. We're going to go ahead and take our time through it. And I believe it'll be the last topic before the final exam. So we'll have one more test, which will be on this next topic. And then after that test will be the final exam, which is cumulative over all 3. So that's what we're going to do next time. We're going to work on the start into that. So I guess for the next couple of days, you don't have any work from me to have to worry about. But if you have no questions, you're free to go, and I will talk with you next time.
Professor?
Yes, ma'am.
Okay, so what if like for one of the answers we're off by like 2 numbers?
I can't say, just, generally speaking. I'll look at your work, and I'll
Okay.
see if it's just like a calculator mistake or something like that. It's not a big deal. But of course, if the answer is wrong by a few numbers because you did something wrong, well, that's a different story. But I always get special credit and stuff like that. And if it's like, let's say 1.467, if you have 1.464, well, that's right. It's the same number to me. But if you have, 2.367, well, that's a significant difference. So it depends on the specifics, but when I go to grade, I'll look at your individual stuff. And, if you did everything right, then you're going to get the vast majority of the points for sure.
Okay, thank you.
You're welcome.
Professor,
Yes, what's up?
I had emailed you the day of the exam, and I just wanted to make sure that you got my exam. I couldn't submit it through Canvas because it kept saying submission failed, so I just emailed you through Canvas.
All right.
And sent the pictures. So I just want to make sure you got it.
Yes, I'm looking on my phone right now. I have an email, and it shows it has the files attached. So if there's something wrong with them, I'll email you again. But one thing I might do, just to make it a little easier in terms of how things are graded through Canvas, or how I grade things through Canvas, I may extend a deadline for you to just try to submit these files in one more time and see if it lets you. And if it doesn't let you again, then yeah, I do have them in my email, and I'll be able to download them if necessary. So I'll do that. I'll extend a deadline, send you an email, say, hey, look, by tonight, send these same files you sent me, and see if you could submit them. And we'll go from there.
Okay, because I was just worried. I tried to do it over my tablet and it didn't let me go through it. So I tried to do it over the laptop and it kept saying submission failed. So my last option was to
Yeah.
do it over my cell phone and it went through, but I didn't know if you got the email.
Yeah, I got your email. So we'll try it one more time through the Canvas system itself. And if it doesn't work, no big deal. Like I said, I do have your email, so it'll be fine.
Okay, thank you.
Alrighty.